Hi, Algebra 2 Trig students. It is Mrs. Leopold here, and I won't be in class today. I'm at professional development on campus, which is why I'm going to be sharing this information with you via video, and you can refer to it, of course, anytime. So first I'm going to review what we did last class, which is the even and odd functions, and then I'm going to take us into our new lesson. So there were two aspects that we did last class with even and odd functions. One is we talked about it visually, so that's why I have the graphs here, and then we're going to move into algebraically because we didn't do a lot with that last class, and I just want to make sure I emphasize it again because we will be looking to test you on that when you look at the assessment. So even and odd functions, this first one, hopefully you look at it right away and you're saying to yourself, oh, that is in fact an even function. Remember, this is an even function. How do we know it's an even function? Well, an even function visually reflects over the y-axis. So it's reflective over the y-axis. So what you see on the right-hand side, if you folded your paper down that yellow line or that blue dotted line, you would get the same thing and they would overlap each other. For our second one, hopefully you remember that there are two lines of reflection for an odd function. This is indeed an odd function. We are going to reflect over both of the y-axis, and we are going to reflect over the x-axis. So this point here is going to reflect over the y-axis, and then it would reflect over the x-axis. Or you could reverse it, reflect over the x-axis first and then the y-axis, but regardless, that's what happens. So that means when we started with our ordered pair of x, f of x, that means when we put in the opposite of x, we get the opposite of y. For our first one, when we put in the opposite of x, we got the original y. So if I'm starting here with 2, 3, when I put in the opposite of x, I got the same y value. Here, if I started with 2, 4, when I put in the opposite of x, I got the opposite y value. And also remember, we refer to these as inputs and outputs. The last thing we did in class, or not the last thing, but another thing we did in class visually with even and odd functions was we had you sketch graphs. So could you complete the right-hand side of this graph if we asked you if it was even or odd? So that was the last thing that we did visually for you to come up with the rest of the graph based on whatever the instruction was. So down below, just reminding us of what we were saying about inputs and outputs. It says, this was our synthesis. Use the language of inputs and outputs to tell us what is true about even functions. And what we would say about even functions is that opposite inputs have the same output. So just to recall, opposite inputs have the same output. And you can see from our example above, that is what happened. And then the language for using inputs and outputs for odd functions is that opposite inputs have opposite outputs. So opposite here. So they both are opposite, right? So opposite inputs lead to opposite or have opposite outputs. Now that led to us writing a sentence algebraically or algebra writing a sentence here about even and odd. It says if a function f is even, then we know that when you put in the opposite input, we will get the same output. So if you put in the opposite of your original x value, you will get the same y value if it's an even function. So your x-coordinate, y-coordinate, when you put in the opposite, you'll still get the same y. That's what an even function does. For an odd function, when you put in the opposite input, you will get the opposite output. So your original ordered pair, when you put in the opposite of the original input, you will get the opposite white output. Now, we then did some algebra questions. We looked at them on Desmos. We decided very quickly and easily on Desmos if these functions were even or odd. And then I took you through these two examples on the board, and we proved whether or not they were even and odd using these two examples up here. And I want to emphasize that because that is going to be an expectation that you must be able to do on your future assessment. So if we look at this first example, the other thing that we did, if you recall, is we kind of noticed that when the exponents were all even, or when the exponents were all odd, we knew if that function was even or odd. You might say, hey, wait a minute, in this first example, why are they all even? Well, remember this is x to the 0, and 0 is also even, and this had an invisible exponent of 1, and both of those exponents are odd. But you still have to prove this algebraically, and if you don't, or you can't, then you are not going to get full marks on the algebra process. So how do you prove it algebraically? Well, we need to put in the opposite input. So I need to change all of my x's to negative x's. So everywhere you see an x, I need to change it to negative x. So notice what I did here. I kept the 3, I kept the 2, I kept the 1, but anywhere there's an x, I parenthesized it and put it to the 4th power. I parenthesized it, put it to the 2nd power, because I'm replacing the positive x with the negative x, because I'm inputting the opposite value. Now you need to show work and do some simplification for this. So we talked in class about if we take a negative x to the 4th power, that means negative x times negative x times negative x times negative x. And when you take a negative to an even power, it turns that value into a positive. So this changes back to a positive value. Same with negative x squared. A negative x times a negative x is just x squared, but we have this negative 2 in front. So we're multiplying negative 2 times the x squared. And then finally, we have our plus 1. So we're going to do our plus 1 here. And what do you notice that we get? Well, hopefully you are noticing that this final statement after I did my simplification is the same as the original function. So that led me back to the same exact function that I had originally. So your conclusion is that this function is even because when you put in the opposite of x, it resulted in you getting the same y value or the same original function. So therefore, you can now tell me it's an even function. So you must do these steps. Step number 1, you must substitute in negative x. Step number 2, you must simplify the function. And step number 3, you must write a conclusion. So this was step number 1. I substituted in negative x. Step number 2, I simplified the function. Step number 3, I showed that when I put in the opposite of x, I got the same original function. And then I concluded with, therefore, now I know it's an even function. So let's try the same process for the next one. Step number 1. I am going to substitute in a negative x. So everywhere I had an x, I'm going to put a negative x, negative x, negative x. Now I'm going to simplify this function. Well, a negative times a negative times a negative makes that become a negative x to the 3rd power. And then, of course, here, this double negative, a negative minus a negative x, turns that into a positive x. And so now I have negative x cubed plus x. Well, to help yourself at the beginning, if you know it's going to be odd, you might want to take the opposite of the original function. If you take the opposite of the original function, right, I put in this negative sign here. So when I take the opposite of the original function, I put a negative in front of this. I have to group it in parentheses, and then I distributed my negative, and now I can see that what I got and what is the opposite are the same thing. So therefore, this now equals negative g of x. I just proved that. So if you put in the opposite of x and you get the opposite output value, if you put in the opposite input value and you get the opposite output value, that now means that you have an odd function. So because this is true, that when I put in the opposite input value, I get the opposite output value, that means now I have an odd function. So this is my conclusion. Step number 1, substitute in negative x. Step number 2, simplify. Step number 3, write a conclusion statement. You must include all 3. Now I want you to try these on your own. Okay, so again, you can pause here, try these on your own. The substitute should hand you a worksheet with all these on there, all the equations, because we didn't get to them, with some space. So you can try them on your own. You already know if they're even and odd because you have it in your notebook when we looked at them visually on Desmos. So you know what your answer is supposed to be, but now I want you to practice the algebra. So again, step number 1, substitute in the opposite input. So substitute in negative x for all of the x. Step number 2, simplify the function, whether it's g of x, f of x, j of x, whatever it is. And step number 3, write a conclusion. So you must write a conclusion that then tells me if it is even or odd. So pause, try it on your own, then you can quickly turn back on the video and it will just have answers only so you can check your work. Okay, here are the answers. You can see I put step 1, 2, and 3. You need to have those conclusions. The first 2 were even, 5 and 6 were neither. 6 was a little more complicated. You might want to distribute to show that it's not going to work. But I also wanted to point out, just so you know, so I think it's good for you to know ahead of time, like if you look at this function, I knew it was neither to begin with. If you distribute, right, if I were going to go ahead and multiply x times x to the third, I would get x to the fourth, x times negative 1, I would get negative x. Well, that's an even exponent with an odd exponent. And when you have a combo of even and odd exponents, you will get it ending up being neither a positive, neither an even function nor an odd function. So that might give you a little hint. So if you were to expand this and you see even and odd exponents, you would also know that it's going to be a neither an even function nor an odd function. So that's our review. Finish the rest of that worksheet. Try to prove everything algebraically. Again, you know what the answers are, but practice these steps. Substitute in the opposite of x or opposite input, simplify the function, and then write a conclusion based on your simplification. All right, now we're moving on to day 4. So Unit 5, Lesson 1. You can open your books to this page so you know. So that is now on page 30. So you can open your books to page 30. And the first thing I just want to draw your attention to is what our goal is for the day. So it says, let's express transformed functions algebraically. So hopefully you're saying to yourself, we've already been talking about transformations. I know how to do that. I know how to show you what transformations are using function notation. We've been doing that the whole time. So really this algebraically might be what is new. So that is going to be referring to this expression. So when we say that we want you to show it algebraically, we're referring to this part of the table below is the expression. So we're now going to give you trigonometric functions. So here, not trigonometric functions, apologies. We're just going to be giving you functions, and then you will be substituting in that function notation into the equation or expression. In this case, you're not going to write g of x each time. So it says complete the table below to describe. We're going to start with the description of the translations. Then you're going to write that in function notation, and then you are going to take this parent function. This right here is called the parent function, the square root of x, which looks like this, right? If g of x equals the square root of x. Then when you plug in 0, you get 0. When you plug in 1, the square root of 1 is 1. When you plug in 4, the square root of 4 is 2. So when I plug in 1, I get 1. When I plug in 4, I get 2. So remember, it looks something like this. That's the square root of x function. So I'm going to take that function, and it says my description in words. I'm going to translate that function left 5 units. So function notation, this is how I would indicate that. Remember, we do the opposite, so I would put x plus 5. Well, if my parent function is the square root of x, I'm no longer going to just have the square root of x. I'm going to put the square root of x plus 5. So I'm replacing this whole x component with whatever is in here. So that's x plus 5. So look at the next one. It says translated, this graph has been translated left 5 units and down 3 units. So this time they showed you here what it would be using the square root function itself. So algebraically they showed it to you. So what would that look like in function notation? So hopefully you're going to know that would just be plus 5 and minus 3. Now look at the next row. This time they showed you what the function notation would be. We're putting in the opposite input, and then they showed you what it would look like in the algebraic expression. So it would become the square root of negative x, but how would you describe that using words? So what would you say? So hopefully you're doing that on your own right now, but that would be a reflection over the y-axis. Or reflected over the y-axis, right? So that's your horizontal reflection or reflection over this y-axis right here. So it'd be looking in that direction. The last one. So we're taking our function. We are going to move left 5 units. So we take our x and we move it left 5 units. So we do the opposite. Then I'm going to go down 3 units. So we go down 3, we subtract 3 from the y values. And lastly, we need to reflect it over the y-axis. Well, we just said a reflection over the y-axis is changing our x and changing it to its opposite. So the positive value becomes negative, but the y values stay the same. So that is how we would do that. So then what do we have here? We would have negative x plus 5 underneath the square root sign. Oops, that should not be a plus 3. And then minus 3. Now this last one we're going to talk about because this gets a little tricky. It depends on the order in which you write this description. So I could get to the same graph with writing a different description. I could get to the same graph writing this function notation and expression notation differently. So we are going to look at that on the next slide. Okay, I want to look at this function a little more carefully and show you that the order in which you state these transformations and how they connect to what is in function notation, which then easily translates to your actual algebraic expression. But the order in which you say these transformations really does matter. And we're going to look at that right now. So it says, first we're going to take, I did 3 points, so you can see according to my Desmos graph here, the black is the original parent function, right? So your parent function is the square root of x. So that is in black over here on the right hand side. I put 3 blue points on that function. If I follow these instructions, it says I'm going to move to the left 5, so 1, 2, 3, 4, 5, down 3, 1, 2, 3, and then I'm going to reflect over the y-axis. So this was 5 units to the left, so now I'm going to reflect, and I'm going to go 5 units to the right, and so that point became there. So I can see that it works. Let's try one more. If I start at this point, I go to the left 5 units according to the instructions up here. So I go left 1, 2, 3, 4, 5. I go down 3, 1, 2, 3, and then I reflect. This is 4 units, so I have to go 4 units over here. Yes, that point works. So I can see that this is, in fact, according to Desmos, accurate in how I translated the words into function notation into my algebraic expression. But I can get that same function by just changing the language. So if I change the order of my description, then I could have a different function notation and a different, so I could have something different here, and I can have something different for my algebraic expression as a result. So sometimes you might see some resources where they factor out that negative and it looks something like this instead. So I factor out this negative, and if I factor out the negative here, this negative goes out in front. Then what am I going to have? This x changes to positive x, this positive 5 changes to negative, so if I were to distribute, I would get negative x plus 5. So I'm taking the reflection and putting it on the outside. Now, if you do that, that is going to change the function notation as well. So we should then have the square root of negative, then you put your parentheses of x minus 5, and then you have your minus 3. Now that no longer means that we are going to do these transformations in the same order. This time, so because if I did that, this is now a right 5, right? If I went right 5, do a different color. If I went right 5 from this point, and then I went down 3, and then I reflected, I would be over here, and that is not what the graph wants us to do. So that wouldn't work. So I'd have to change the order in which I describe those transformations to get to the same graph. So this time, I could still start with, no, I should change it to start with my reflection. So I'm going to say first I'm going to reflect over the y-axis. So that has to be my first step. And then you can do your transformations in any way you want. You can go right 5 and down 3. But notice that has to change to a right now. So if I take this point here and I reflect first, so I reflect over the y-axis. So I go 5 away and then I go 5 this way, so I'm here. Then I go to the right 5, 1, 2, 3, 4, 5, I'm back here. And then I go down 3, 1, 2, 3, I end up here. Oh, sorry, I was on the wrong one. I was like, that didn't make sense. So I'm here at 4. I go to the left 4, so I reflect, and I go here to 4, apologies. And so sorry, that reflection, I did that wrong the first time. So I'm reflecting over my y-axis, as it says here, reflect over the y-axis. Then I go back 5 units, so I'm here. Then I go down 3 units, and that takes me to this point here. I do my next one. Let's start here with this point. First, I reflect over the y-axis, so it's 1 unit away, so I go 1 unit away here. Then I go to the right 5, 1, 2, 3, 4, 5. Then I go down 3, 1, 2, 3, then that would put me here. So now I can see that this is also representing the same graph as our original, but I had to change the order in which we would get to that point. Now, you might be asking yourself, why do we have to change that order? So that is a little bit confusing. So I'm going to just show you something really quickly, and I hope this helps, but you might just want to pause and ponder it a little bit too. Let's say instead you wanted to stick with the translations. You wanted to say, okay, I want to go right 5 and down 3. So I want to go right 5. I want to stick with my translations first, right 5 and down 3. I would go right 5, 1, 2, 3, 4, 5, and I would go down 3, 1, 2, 3, but I'm going this direction now. I'm still going this direction because I haven't done any reflection. You can no longer say you're going to reflect over the y-axis. You're not reflecting over the y-axis anymore. You're actually reflecting over the x equals 5 line. So you could say you're reflecting over x equals 5, because essentially what we've done is we've taken this origin, which is here, and we've made it right 5 and down 3. So this is my new origin. And now instead of reflecting over the y-axis, this isn't the y-axis anymore. I've made x equal 5 my new y-axis. So you could also say right 5 down 3 and reflect over the x equals 5 line, in which case it would take the graph back this direction and you would get here. I know that's a lot of information. Play around with Desmos, play around with the order, and see how it goes. Okay, first we have a little reminder here. What is this function? F of x equals x squared. That's the parent function. That is a parabola where the parent function, that means the original vertex is at the origin 0, 0, and then we make our parabola from there. It's reflective over the y-axis because it's symmetric. So if you know that, then the rest of this information is going to be a little bit easier to do as we go through the rest of the steps. So you might want to write yourself a little note to remind yourself that's the parent function and what a parabola looks like and where the original vertex is. So it says write an equation for the function g whose graph is the graph of the function f translated 3 units to the left and 5 units up. So g will now be 3 units to the left and 5 units up. So remember, left means we're going to do +3 and up means +5. Now, if I want to write that as an algebraic expression, I am now going to put the x plus 3 in for x. So x is right here. So now that x plus 3 becomes squared. And then I just put the +5 out here. So now my g of x function equals this right here. So g of x equals x plus 3, the quantity squared, plus 5. Where is your vertex? Well, if we were at 0, 0, and we moved 3 units to the left and 5 units up, then from 0, 0, I'm going to go 3 units to the left and 5 units up. So my new vertex is up here. So hopefully you're saying to yourself, that's just -3, 5. So you can see here my vertex is at -3, +5, because this means 3 to the left and this means 5 up. Okay, what if we gave you this vertex instead? Well, hopefully you're making a connection between what the vertex is, where those points are, and if this is the ordered pair that's the vertex, can you go backwards? So we have a function h of x. We're going to have some x squared. So what are we doing? This is positive 1.5. So we're going to go to the right 1.5 and up 2.6. So going to the right means we have to subtract 1.5, and then going up means we need to add the 2.6. Again, the parent function, so instead of having an x, we are now translating that x to the right 1.5 units. So that's why that has to go inside here in the quantity squared. So try the last one on your own. Pause for a moment and try it on your own, and then you can compare your answer with mine. Okay, so hopefully you got this. Moving to the right, 3.2 units. So we have 3.2. Right, 3.2 means we have the minus sign. Moving down, 4.7. So we have our minus 4.7. And then don't forget this opens downward. Opens downward means a reflection over the x-axis. And if you're reflecting over the x-axis, you must have this negative sign in front. Okay, so now we are at the lesson synthesis. So I want you to try the synthesis on your own. I'm just going to remind you of what these parent functions are. So the parent functions are f of x equals 2 to the x power here. So 2 to the power of x. G of x, our parent function, would be x to the second power. And h of x, our parent function, would be x to the third power. So of course, wherever this x quantity is, you're going to replace or see what was replaced for it to help you identify what kind of transformations were made horizontally. And then anything on the outside, you can kind of help you identify what transformations were made vertically. So pause this video, have a little moment to try to write your sentences in the proper order. Now you can see here the second question says, does the order in which you list these transformations matter? It is going to matter for one of these. I want you to try to figure that out either visually, graphically, and determine which one it does matter for, and then talk about it down below, and then you can check your work with me. So try this on your own now, and then unpause and see how you do. All right, you can check your answers here. On the first one, you should have said reflect over the y-axis and translate up 5 units. For the second one, you should have said translate right 3 units and reflect over the x-axis. And for the third one, you specifically needed to talk about your translation. You could say translate left 2 units, then reflect over the y-axis and translate down 6 units, or you could have done both of your translations, left 2, down 6, and then reflect after that. But that one is the one that mattered. And let's just look at that for a little bit. On your original function, remember this is the parent function right here, h of x equals x cubed. So this is your parent function right here, your x coordinate and your y coordinate. If I plug in 0, 0 cubed is 0. If I plug in 1, 1 cubed is 1. So we're just going to go with those 2 points. Now look at the transformations that took place here. If you notice the way I listed them, I said we're going to go left 2 units, so left 2. Then I'm going to go down 6 units, 1, 2, 3, 4, 5, 6. And then I'm going to go reflect over the y-axis, so I'm at 2, so that point would be over here. So this point, I'll make it a different color, at 0, 0, now became this point here, right? So let's make sure I did that correctly. So this ordered pair is 2, negative 6. So if I were to plug in a 2 to our new function, then I should get negative 6. So 2, that would be a negative 2 plus 2, I cube that, and I subtract 6. Well, negative 2 plus 2 is 0, 0 cubed is 0, so that would in fact produce negative 6. That means my descriptions are accurate because I followed that on the graph according to my description. I checked it algebraically here according to what was listed in my function notation in the graph. So let's try another one. If I do this point here, according to my description, I'm going to translate left 2 units, so that's left 2. So I'd be here, sorry, left 2. Down 6 units, so 1, 2, 3, 4, 5, 6, that'd be here. And then I reflect over the y-axis, so that's 1 unit here, 1 unit here. So it looks like that would be 1, 1, 2, 3, 4, 5. It would be 1, negative 5. So that means if I plug in a 1, sorry, and this didn't make sense here because this, like you can see I plugged in a 2 here. If I plug in a 1 though, I should get negative 5, so let's see what happens. So if I plug in a 1, I would get negative 1 plus 2, I would cube it and subtract 5. Negative 1 plus 2 is 1, 1 cubed minus 5 is, or sorry, 6. Oh, phew, this it doesn't work. I knew I was supposed to get 5. So 1 minus 6, sorry, I'm going back up here. I wrote that down incorrectly. So 1 minus 6 is indeed negative 5, so that means, once again, my description is accurate because I followed it visually in this graph, and then I did the math algebraically to make sure that the points I did based on my description were the same points as I got algebraically. My point then is saying that what if you had said reflect over the y-axis and then do your translations? So if I took this red point and we won't do the red one because that doesn't work. If we took the green point up here, I'm now going to make it blue. And first I reflected over the y-axis, so I would go 1 to the left, so I'd be here. Then I moved left 2, so I would have to go 2 more to the left, and then I would go down 6. Do I end up at this same point over here? No, I don't. It's incorrect. And when you did the math, you wouldn't get negative 3, negative 5. This is incorrect. So your description should match the math, and everything should go together. So again, just take some time, maybe practice in your homework, try to let that sink in a little bit, but this order now in which you describe these transformations does matter. We're going to do one more thing today because we want to save some time for Monday so you have a little more time to talk about dilations. Okay, our final part of this lesson today, we're going to skip to the last lesson to try to give us more time on Monday to do the dilations together. It just makes a little more sense. So I want you to flip your booklet to page 41 now. So on page 41, you can find this first example. We're going to skip the word problem on the left. We're just going to jump into 41. But what are we doing? Our goal in this particular unit, this particular lesson, lesson 10, is to make some new functions using other functions. So our new function we're trying to make here is s of x. So we're trying to make this new function s of x. using the function e of x and the function L of x. So we can see e of x graphed. I've color coordinated it for you. So we have the e of x graph there, we have the L of x graph, and we're trying to we want you to sketch a graph that will be s of x. So what do you think s will look like? Well, really, what are we doing to those two functions? We're just adding their y values to each other, their output values, right? These are your input values. So if I take the input values and I get outputs here and here, what am I doing to those two outputs? I'm adding them together to get my s equation, s function, and then I'm gonna sketch a graph of what that result would look like. So I listed some x coordinates just so we could have a look. So e of x at -2, so if I go to e of x -2, it looks like that value is about 7. If I go e of x equals -1, the x value is about, the y value is about 3. E of 0 is about 1. E of 1, I don't know, maybe we'll call it 0.25. And e of 2 is teeny tiny, maybe I'll call it 0.1. Just an approximation, right? It's really, really close to 0. And then they're continuing to get closer and closer and closer to 0. So how much impact is that really having? Let's look at our L values. So when I plug in -2, my L of x, L of -2, looks like it's -2. When I plug in -1, L of -1 is -1. L of 0 is 0. L of 1 is 1. L of 2 is 2. Well, notice here it defines what s of x is. S of x is these y values added together. So I'm going to add those together. 7 plus 2, -2 is 5. 3 plus -1 is 2. 1, 1.25, 2.1, etc. So let's just graph those. So when x is -2, s of x will be 5. So -2, 5. When x is -1, we get a 2. When x is 0, we get 1. When x is 1, we get 1.25. When x is 2, we get 2.1. So as these values get closer and closer to 0, they're not going to, and you add those values onto the L, it's pretty much just going to look very linear in your end behavior. So you have to fill up the graph and take it all the way, right? Because as you're adding 0.01, 0.001, 0.00001, we're adding that to all of these values, to 3 and 4 and 5 and 6. It's just going to look linear by the time you look at that end behavior. It's going to be really close, and then it's going to turn and go up this way. So these are negative values as we continue, but we're off the graph here, so you're done. So this sketch here, the blue sketch, is what you would have for your final answer for s of x. So that's it. That's e of x plus L of x. So we've used two functions to help us identify what the third function s of x would look like. So you can try these two on your own. So go ahead and sketch them now, and then you can compare them with my answers, or you can look at the answer key and just see how you did. Okay, do your graphs look something like this? Again, we're just here, all these y values are negative, right? So we're subtracting every single y value here. We're adding a negative, so adding a -1, consistently adding a -1, I just moved down every single y value I saw. I just moved it down to 1 and did the new one. So the blue is what you should have graphed for your final solution of e of x plus m of x. And over here, the blue is what you should have had. So these are so close, these y values here on this graph, that it's barely going to change anything. And then these y values are growing, but we're off the graph, so you can't really have much of an impact. It's just making this graph go a little bit higher. So the blue, again, is what you would get if you added those two graphs together. If you added e of x plus p of x. So you can finish the rest of that page. That's really it for this particular section, and then do the homework, of course. And then the two sections in between lesson 8 and lesson 9, those are on dilations, horizontal and vertical dilations, and that is what we're going to do on Monday. Then you have a break over Chinese New Year, Lunar New Year, so please make sure you do a little bit of math, or it's going to be really hard to come back and review and take the test that same week you get back. I hope this helped. Please email me if you have any questions. Have a great weekend, and I'll see you soon. Bye.